what is Wien's law in physics is what we would understand in this lecture. Now, Wien's law is a very simple concept where we say that the wavelength of the peak of emission is inversely proportional to temperature. Now, to understand Wien's law, let's first understand the simple principle where I say frequency works inverse with wavelength. Now, since frequency works inverse with wavelength and the peak of emission wavelength is inverse with temperature, therefore I can say frequency works directly with temperature. That's a simple way that I can prove it. So under the Wien's law, I can say the peak of emission, the maximum of the peak of emission wavelength would be equal to B by T, where B is the Wien's displacement constant. Now, Wien's displacement constant is 2.89 multiplied by 10 raised to power minus 3 meter Kelvin if I want to have the values of wavelength in meters. However, in case of optical wavelengths, we usually understand it in nanometers. So, it is 2.89 into 10 raised to power 6 nanometers Kelvin. Clear? So, this value of the wavelength would be in nanometers. So, based on what is the value of B, the constant, we can find whether the wavelength would be in meters or nanometers. So, that thing is clear. Then, T is the temperature in Kelvin. Okay, and therefore we say the B, which is the Wien's displacement constant, is meter per Kelvin. So, Kelvin would cancel out and we would have the wavelength in meters or nanometers, whatever the constant you have taken based on that. Now, the most important thing about Wien's law is that, as we can see in the diagram here, as the wavelength reduces, understand this diagram carefully, as the wavelength reduces, the temperature increases. So here the temperature was, when the wavelength was higher, the temperature was relatively less, but as the wavelength increases, the peak of the emission wavelength, we would see, as the peak of the emission wavelength reduces, we would see that the temperature rises, and therefore we say that the peak of the emission wavelength is inverse to the temperature. That's the first rule that we need to understand. So I hope with this we can understand and derive these two concepts clearly. Now, as the temperature increases, as you can see, moving this side, the temperature is increasing from 3500 to 4000, 4500, 5000 and 5500. So as the temperature is increasing, the light changes from red to yellow to white and finally to blue. With higher temperature, the colors changes towards blue. And this is with increase in temperature. Clear? So this is why we understand Wien's law. Now note, when the Planck's radiation law was given, based on the Planck's radiation law, we understand that the derivative of the Planck's law are two derivatives. One is the Wien's law, the other is Stephen-Boltzmann law. We would understand Stevens-Boltzmann law in a separate lecture. But under Wien's law, the basic idea was an inverse relation that exists between wavelength and temperature. So as the temperature rises, the wavelength reduces, or as the wavelength reduces, the temperature rises, as we can directly depict from the graph given here. However, the second rule, which is the Stephen-Boltzmann law, has nothing to do with the wavelength. It focuses on energy directly proportional to fourth power of the temperature and energy having a direct relation to area as well. So, two things that were mentioned under the Stephen-Boltzmann law. We would cover that in a separate lecture later on. But this lecture was dedicated to Wien's law. The numericals would be very simple. Directly you would have the value of B and temperature given. You would have to find out the peak of emission the wavelength of the peak of emission, and that's what the direct questions would be. The only thing you would have to take into account whether you take the value of Wien's displacement constant in meters or nanometers. Usually that's mentioned in the question clearly, and therefore it should not be a trouble. And the next important thing under Wien's law is a theoretical question which directly comes on the fact that wavelength of the peak of emission is inverse to the temperature. However, the frequency varies directly with the temperature, and therefore we can see as the temperature increases, the color increases. So that was about Wien's law for today. Stay tuned for updates on physics and other subjects. Have a wonderful day.